Hello! For this week's JavaScript project, I'm going to show you a basic implementation of the WISARD architecture that was the subject of last week's video. As always, this will make the most sense if you've seen the theory video that this example is based on, so there will be a link to that video at the end and again in the description below. You'll remember that WISARD was a pattern classifier based on addressable memories, the sort of things that make up computer memory chips. In the video, I showed it being used to classify simple, low-resolution images, consisting of binary ones and zeros on a square grid. However, WISARD can be used to classify any pattern consisting of a number of binary bits. Whether it's used to recognize images or some other signal, the process is the same. You present an example of a pattern that you want WISARD to learn, instruct a group of memories called discriminators, corresponding to the class of pattern to learn it, and then repeat the process for other patterns, or other examples of the same pattern. Then, when WISARD is called upon to classify an unknown image, the image is presented in the same way, and the discriminators are let loose on it. The class with the highest number of active discriminators gives WISARD's choice. Let me clear that up with an example. An example WISARD system might be used to recognize employees at a factory when they face a camera. Here are images from 3 employees which have been hard limited, so they only consist of black and white pixels, the binary ones and zeros that WISARD needs. We lose a great deal of the detail, but with luck retain enough for WISARD to be able to tell them apart. WISARD in this case will consist of a set of discriminators for each employee, say 100. The employees are the classes in this case, and the images on camera, after hard limiting, are the patterns which could belong to those classes. Each employee is sat down in turn in front of the camera, and the set of discriminators corresponding to that employee is told to learn that image. Each of the 100 discriminators is told to produce an output signal of 1 whenever they see that particular image. For instance, when Fred is in front of the camera, the discriminators corresponding to Fred are programmed so that they each produce a 1 for that image. If they saw the exact same image of Fred again, they would all produce a 1, giving that image a unanimous score of 100 for Fred's discriminators. Similarly, the discriminators for Myra and Ted are trained to produce perfect scores for images of Myra and Ted, respectively. One of the employees then returns to the camera and produces a slightly different image. After all, no 2 images of the same person can be absolutely identical. The sets of discriminators for each employee are given this new image and score it. The employee with the highest score is the person recognized. In this case, WISARD is fairly certain that the person in front of the camera is Fred. If all the scores were below a certain threshold, then the person facing the camera would be reported as someone unknown. That's effectively what WISARD does. For more details on how it does it, you need to see last week's video. Here's the screen that you see when you activate the program. The small grid in the top left corner is where the classes of patterns and the test images are formed. You move the mouse over it and click to turn a square black, equivalent to 1. Similarly, click on a black square to turn it back to white again, equivalent to 0. Below the grid are buttons for running the discriminators on a test image, for saving and loading the discriminator data, more on that later, and for clearing the grid. The demonstration, as I've set it up, allows for 4 classes of patterns, and you can see an entry for each of those below the buttons. For each class, the left-hand text field allows you to specify a name for that class. Just type the name in, and it will be saved along with the discriminator data when you click on Save. The right-hand text field is where the results of running the discriminators appears. Lastly, each of these classes has a Learn button, so that you can tell WISARD to learn a particular pattern on the grid as a member of a particular class. The purpose of the box marked Save Load will be explained later. An example should make this clearer. Here I have trained 2 classes, one for smiley faces, one for sad faces, as the names show. I presented one smiley face on the grid, then clicked on Learn for the first class. Then I presented a sad face and clicked on Learn for the second class. Finally, I drew a slightly different sad face and clicked on the button called Run Discriminators. Each class in this system has 20 discriminators, and 14 of them were activated for the sad face. 11 of them activated for smiley face, and that's understandable since the smiley face and sad faces had several pixels in common. Still, if WISARD had to choose, it would say that what you're looking at is a sad face, and I think we can agree that it's got it right. Here are the global variables set in JavaScript. Num rows and num cols determine the size of the pattern grid, 10 rows of 10 columns each, 100 pixels. The system is fairly simple and assigns grid values to inputs on discriminators on a one-to-one basis, so there must be 100 input lines for all the discriminators in each class. If there are 10 discriminators per class, each must have 10 input lines. If there are 4 input lines per discriminator, then we would need 25 of them. I have gone for 20 discriminators, so each must have 5 input lines. The reason I opted for a one-to-one relationship between input lines and pixels is to make the program simpler. If there were redundancy built in, then more complicated code would be needed to assign those input lines to pixels. Num classes, of course, gives the number of pattern classes that can be recognized. These global variables are defined in a JavaScript block in the header, as they are needed for displaying the screen itself. Here's the HTML code for displaying the pattern grid, and you can see that the donkey work is done by a JavaScript block using multiple calls to the built-in document.getElementById function. It needs to know how many rows and columns there are, so those variables must have been defined previously. The JavaScript code is contained within an HTML table, and a nested for loop is used to create the required number of rows for that table, enclosed within tr and /tr tags. The grid cells themselves are small square graphics, called 1.png for a black square and 0.png for a white square. Each of these graphics is given a name, which is the letter P, followed by the row and column separated by an underscore. The name is necessary so that the code can change that graphic from white to black and vice versa. Each graphic is also given an onClick property, which calls the function choose to make the change and take note of the result. Incidentally, I have stuck to using row and col as for loop variables throughout the entire program. Similarly, I use the variable c as a for loop counter that goes through all the classes, and d as a for loop counter to count through the discriminators for any given class. Here is function choose. It simply alters the state of the grid element given by the row and column from 1 to 0 or vice versa. Then it alters the graphic on the screen appropriately. Here's an example of that. Just underneath the code to display the grid is a similar block of JavaScript code to display details for the given classes. Again, this is used to construct rows of a table. The first cell in each row is a text field named Pat, followed by the class number, which will hold the class name if the user specifies one. The next cell contains a text field named Count, followed by the class number, into which the number of activated discriminators will be written. And then there are 2 buttons, one to get that particular class to learn a given pattern, and the other to clear all the discriminators for a given class. Both these functions need to get the class number as a parameter so they know which one to alter. We need to set up a few more global variables, but they can be done in the main body of the code. The variable PWR gives 2 to the power of the number of address lines, and will tell you how many slots each discriminator has. If each discriminator has 4 input lines, for instance, that will specify 2 to the power of 4, i.e. 16 different combinations, each of which must be represented by a 1 or 0 inside the discriminator. Similarly, if the discriminator has 6 input lines, then it must have 2 to the power of 6, i.e. 64 elements. The variable GD will hold the pattern grid. It's a one-dimensional array at the moment, but we're going to turn it into a 2-dimensional one fairly soon. That will be done by function clearGrid, which we call. The variable CLS is an array which will hold the classes, consisting of all their discriminators and what have you. They will be set up by function initializeClasses, which we also call. The array nums is used in assigning pixels on the grid randomly to the input lines of discriminators. I'll explain why we need that in a minute. Finally, the variable lines and ln will be needed when loading in data. They have to be global, so we set them up here. More on them later. Here's function clearGrid. Each element in variable GD is set up as an array in itself, which will hold one row of the grid. Each element of the two-dimensional array that results is set to 0, equivalent to a white square on the screen. Also, the squares are reset to the 0 image. This is because one of the buttons on the screen is used to clear the grid, and we want the whole thing to turn white when you click the button, even if it's covered in black squares. Remember that array nums? Here's why we need it. All the pixels in the grid are assigned at random to all the discriminators in each class, and because the number of discriminators times the number of inputs per discriminator is the same as the number of pixels in the grid, each input line is guaranteed to get one and only one pixel to itself. Tying up address lines with pixels is easy to start with. You go through all the discriminators, choosing random numbers in the grid to link to the discriminators, ensuring that the same pixel doesn't get picked more than once. And there's the problem. Every time you pick a pixel at random in the grid, you have to make sure that it hasn't been picked before. Not a problem in the early stages, but it gets harder and harder as the pixels get assigned, until eventually the code has to pick dozens, if not hundreds of random pixels, simply in order to land on an unassigned one. There is a simpler way, though. This is where array nums comes in. Instead of taking wild stabs at the pixels in the grid, finding it ever harder to score a hit as we go on, we get a list of numbers representing the grid elements in random order, and work our way through that. If there are 10 rows and 10 columns, that's 100 numbers. So we take the numbers 0 to 99, always start counting at 0, and shuffle them. That will give us the list of pixels in a random order. That's what function randomList does. It first gets all the numbers in order using a for loop, then performs a large number of shuffles. I chose 1,000, swapping 2 of the numbers randomly each time. After that, to get the list of pixels in a random order, just work your way methodically through array nums. I'm sorry, when it came to putting up function initialize classes on the screen, I either had to display it at a font size that would make you squint, or split it rather inelegantly into 2 columns. At least this way you stand a fighting chance of being able to read the code. Function initialize classes sets all the pattern classes to blank, and sets up the connections between the discriminators of each class and the pixels on the input grid. As such, it uses for loop variable c to go through all the classes in turn. First thing to note is that function randomList is called within the for loop, i.e. the pixel values are reshuffled for each class. This is to ensure that discriminators for each class don't have the same pattern of connections as other classes. The variable x is simply a counting variable that starts at 0 and will go through nums 1 index at a time when we need those values. Then for each class, we go through all the discriminators in turn using a for loop variable d. Here I'm going to use a JavaScript structure I don't need usually, called a set, but it can be just the ticket if you want to tie various different items together in one bundle. The discriminator will need a set of values, called values, and a set of row-column coordinates for all its address lines. The line with the variable dummy is the one that creates a set and assigns it to the local variable temp. In fact, there's nothing temporary about this variable. This is going to be our pattern class, but it's easier to work with a variable called temp and hand the whole thing over to an array element in CLS, rather than having to deal with handsful of array indices at every point. In truth, I don't need the variable dummy. It's just to set up the set and is never referred to again. What we do need to be part of temp is an array called row and another called col. These will hold the row and column for each address line. For that discriminator, we read the number of values from nums corresponding to the number of inputs and turn them into a row and column number using modulo arithmetic. X increases at each step to move along the array nums. Finally, for that discriminator, we set the entire contents of array values to 0 to indicate that the discriminator is blank. Note that we use the limit of PWR to clear the whole of values. And right before we move to the next discriminator, we had everything we have just set up to array CLS, storing it in the appropriate class and the appropriate discriminator. While the variable temp will die when this function terminates, its contents will live on in array CLS. This works because of a quirk in JavaScript. When we create a local variable temp and make it to point to some complex data structure, like an array, anything bigger than a simple variable, then JavaScript doesn't make a separate copy of whatever the thing being referenced is, and make temp point to that. No, it simply makes temp point to the same piece of memory as the original variable. We can change temp as much as we like, and it's that original structure that changes. Effectively, you have some structure in memory that can be referred to using either of two names. Then, when the local variable temp is deleted, the structure stays where it is, complete with the new alterations, and it is just the name temp that dies. Try it by running this small block of JavaScript. The first line sets up a simple array called A, with 5 elements in it. The alert statement displays element number 3 of that array, which comes out as 5. Remember, you start counting indices at 0, so element number 3 is the 4th number that you see on the screen, which is 5. Now the crafty part. We set up a variable called B and make it equal to A. We change element number 3 of array B from 5 to 10. Then we repeat the exact same statement from before. Display the third element of array A, not B. However, the number that pops up is 10, even though we haven't touched A. Instead of creating a copy of A and calling it B, JavaScript simply makes B point to the existing A. Any changes made to B are actually made to A, as the second alert statement shows. It's the same with our variable temp, pointing to some complex data structure buried deep in an array. Of course, we will need a way of translating those row and column values into an actual address inside the discriminator. And to do that, we use function getAddress. It takes the discriminator D as a parameter, together with its set of row and column values. It goes through each of the addresses in turn and uses them to access the grid, taking the 1s and 0s for each square of the grid and turning them into an index slot using the standard doubling and adding 1 or 0 method. What pops out of function getAddress is a number in the range 0 to 1 less than PWR, given the address lines of the discriminator and the current state of the grid. Now that we have a way of turning any grid pattern into a series of slots inside discriminators, the rest is quite easy. Take a look at function learn here. This is called when we want a particular pattern to be learned for a certain class. It just goes through all the discriminators for that class, translates the appropriate grid squares into an address for that discriminator, and sets the slot given by getAddress within that discriminator to 1. Again, for efficiency, we use variable temp to stand in for the element of array CLS that we want. That way we don't have to mess around with double array indices, and it has exactly the same effect. One more important function, and that's function run. In this case, we want to present the current grid pattern to the discriminators of each class in turn, and count how many of those discriminators produce a 1 output. That total will appear as the score of the class in the text field on the screen. For each class C, we set a score to 0. Then we go through each discriminator of that class. The code that translates the grid position into a value inside the discriminator is actually identical to the code that we used to set the value to 1 in the first place, even down to using variable temp again for convenience. Rewind the video a few seconds and check. The discriminator will produce a value of 1 or 0, which will increase the score by 1 or not. Finally, when every discriminator has chipped in, the score is written to the screen. 2 more functions and we're done for this project. Function save, you won't be surprised to learn, allows you to save the layouts of your discriminators, though not, in this simple version at least, the training patterns used to set up those layouts. You'll remember from the first screen a large text area at the bottom of the screen marked save/load. Function save takes all the data and writes it into this text area. You then select it all and copy it to the clipboard, then paste it into some sort of text editor like Notepad and save it as per normal. Function save creates a string variable s in which all the output is built up before being dumped out into the text area. 2 nested for loops go through all the classes and all the discriminators in those classes, and for each discriminator, it adds all the row and column values of address lines to S, followed by all the stored values. These numbers are all separated by line breaks given by the \n characters in the code. Finally, the getElementById function built into the document object is used to copy everything in S into the text area. Function load works in a similar way to function save, but in reverse. Here you open your saved data in Notepad and copy and paste it into the save load text area. Then click load. This is where those two global variables, lines and ln, come into play. Variable S reads the contents of the text area into JavaScript, and this is split into its constituent lines in array variable lines, using the line break character as the line delimiter. Then the double for loop reads those values into the discriminators of the classes in the same order that they were saved. There is a function called getLine, which works together with the line counter ln to give the next line of data at every stage. This is why lines and ln must be global variables. They are initialized in function load, but also used in function getLine. The array lines was set up by the function split, which splits the huge string S into the separate lines. Each of these lines takes the form of a string, even though most of them actually represent numbers. So whenever we expect a number, such as for the stored values in the discriminators, we specifically have to convert what getLine gives us into that number using the eval function. That's why a lot of the calls to getLine are enclosed within calls to eval. I should also point out that if you save data using one setup with a given number of classes, discriminators, and grid rows and columns, and then change those values in the program, then it won't load that data back in successfully. Function load simply assumes that the arrangement of the system is compatible with the saved data. And there you have it. The system is very basic at the moment, but it does demonstrate the essentials of the WISARD architecture. I'm sure you've seen various improvements that you could make already. I've just pointed one out, where the program could check that data you're trying to load in is compatible with the current configuration of the system. Also, clicking on those grid squares can be quite a nuisance, so you might like to put in the facility to save and load grid patterns as well as discriminator data. A few more editing facilities wouldn't go amiss either. In order to save on storage and processing time, I have kept the size of the patterns small. There's not a great deal that you can do on a grid that is 10 by 10. However, I would love to hear if any of you try to run it on larger patterns. Thumbnail-sized images, perhaps. Whatever changes and improvements that you make, please do let me know about them in the comments below. Thank you.